All right, awesome. Good morning, everyone. How are you doing? Nice to see everybody. All right, let's get started. Okay, so today we're going to have a look at how you can do machine learning in Azure Synapse. So let's make sure all my stuff is on and let's go. So just real quick, so bit about me. I run a company called Advancing Analytics, and we do a whole load of bits and pieces. I will call your attention though to our YouTube channel where we've got a whole load of content. So we've got absolutely loads of content on Synapse on there, lots of videos by Simon. Simon is talking later. I hope he's not been on already. He's talking later today, I think, for his comparison of Databricks and Synapse. So go and have a look there. I think we're up to like 75 videos or something. A bit about me. So I'm a Microsoft MVP for AI, and that basically means I just talk at events, like this too often and probably don't do enough real work. But we get around a bit. So my company is a Microsoft partner as well as a Databricks partner. So we do an awful lot in Spark, which is kind of going to be the focus today when we talk about one of the aspects of looking at machine learning inside Synapse. Okay, right. So I'm not going to go through the, what is Synapse. I think everybody's probably seen that enough with a lot of the sessions that we've had today. But I want to focus on, well, how is it that ML actually integrates with, some of these components? So just looking at this picture, right? We've got the analytic runtimes down there, and where our focus is looking at, well, what's the easiest way that we can take a model that either we've pre-built and we can get running with it, or where can we build models? Now, with Synapse, you've got multiple integrations as well into tools such as Azure ML. Now, we're probably not going to cover those today because we won't have time, but then there are other sessions later today looking at how you can do some aspects with AutoML and some of the other integrations into Azure Machine Learning. So the main kind of out-of-the-box interfaces that we have are inside SQL pools. So in the old kind of Azure SQL Data Warehouse style, what we have is the predict function. And so the predict function can give you the ability to, in a normal T-SQL statement, call out to a model that you've deployed, that maybe you've deployed into Azure ML, and then you integrate back in, and you can combine that with your batch data. Now, the other way that you can do that is through Spark, and that's where we're going to focus today. And we're going to be looking at how you can score a model, how you can train a model, and how you can get working, and some of the common processes that you would want to do and things that you'd want to apply to a model. How you can do that at scale inside Spark, inside Synapse. There we go, some of the integration points too, right? So as I said, Synapse contains a whole load of bits and pieces. Now we're just going to kind of focus in the Spark pools area. And so Spark pools are interesting, right? Okay, Spark pools are great. Spark is incredible for enabling you to scale your computation across, as big a cluster of machines as required. We'll go through a little bit in a moment, kind of how Spark works and the architecture behind Spark to give you a bit of context. But inside Synapse, your sessions are kind of built for uptime, and you've got a whole load of different languages that we support there. So you've got Scala. So Spark is predominantly written in Scala, and that's super useful because what we have with Scala is a functional language. And if you think about a lot of big data, what a lot of big data actually is MapReduce operations, okay? And MapReduce sounds like, if you've not looked at MapReduce before, this very grandiose kind of term, but all it basically is mapping a function to your data and then mapping that function to where your data resides on a machine. So because you're mapping a function, it makes a lot of sense to actually build this stuff in a functional based way, which is why Scala was really helpful. But we also have there Python, C#, and SQL. And if you have a look at now, so you've got how Spark was written in Scala, but you have these languages that you can actually interact with it and interact with the APIs. If you look at how much things have progressed in the last couple of years, I think roughly about 2015, we sat at about 80% Scala usage across Spark. Now it's something like about 12% Scala usage, with the rest of the usage being distributed between Spark SQL and Python. So there's been a massive shift towards people just using Python. So do you need to know Scala? Not at all. We won't go through necessarily why, but Spark is written in a declarative way. So you can choose any of these languages you like, and they hit an engine, and then you get your results back. So you don't need to worry so much about which language you're using anymore. You used to have to, but now you kind of don't. So you can use it for a whole load of different things, but we're going to focus on that second one there, right? Machine learning. So Spark can be really complex, right? Spark is an incredible process. It's an incredible framework, but it can be quite complicated. And to get it right, there's a lot that you really need to understand about your data in order to get the best performance from something like Apache Spark. And session management inside Synapse is interesting. We say interesting because it's a bit of a pain. Right, so what is Spark, right? So Spark you can think of as a unified analytic platform, which basically extends into giving you SQL and data frames. So if you've ever looked at something like pandas inside Python or R, where you've got data frames, it's a very similar kind of look and feel. They basically feel a lot like a table inside a database. You've got graph, so graph-based processing, so where you've got highly connected data. Streaming, so where you've got data coming in very fast, from maybe IoT devices or anything else. And then our last one there, machine learning, okay? And each one of these is built on top of Spark Core. And Spark Core is a shared set of libraries that have all of the logic for reading and writing. So you don't need to worry about bolting new things on. It all kind of shares this underlying unified framework. Right, let's talk a little bit about the Spark architecture. This is an awful term that comes from Simon Whiteley. You'll probably see lots more awful terms and Spark-related puns later today. But what we're looking at is we always start off, when we talk about Spark, we're talking about a cluster. And so the thing that drives that cluster is a driver. We've got this Spark driver. And on that driver, you have this thing called the Spark context. And it's this Spark context that tells your cluster, what to do and how to kind of work. So let's say we've got a cluster like this. Okay, I've got a driver and I've got two workers. The workers are what are the processes that are actually going to do everything for us. And on each one of those workers is a process called an executor, and that's pretty much what's doing the work for us. Now we could have a 3-node cluster right like this, or we could scale that out to 5. We could scale that out to as many as you need, right? There are clusters deployed, beyond sort of 6,000 nodes for very heavy computation tasks. And one of the great things about Spark is, so Spark is an MPP engine. It's a massively parallel processing engine. So what that means is that, everything you're doing is being distributed across multiple machines. So if you have a problem, right, of where you're trying to process stuff and you're reaching that upper limit of what you can do with your machine, then the only kind of way that you can go is to scale out. And when you scale out, you have a real elastic scale. So, you can today scale to 2 machines, and then when computation increases and demand increases, right, you then scale to 4 machines, or 8, 16, right, 64. You just scale as much as you need. And then when that consumption demand decreases, you just scale back down and you preserve those costs, right? So one thing worth calling out is Spark at the moment, Spark today, runs entirely inside the Java Virtual Machine, the JVM, okay? And that has a number of complications for machine learning. If you're familiar with machine learning in, say, something in just pure Python or pure R, then some of the processes that you would expect to apply will not scale. And they won't scale because inside that JVM, you basically have a session in there for Spark, and then a session for Python runs ever so slightly externally to that. So there's no built-in way of natively running Python. In order to get Python to work in Spark, it has to be serialized and deserialized, which causes complications for training. So what happens is if you want to just do pure Python-based machine learning in a Spark notebook on, say, something like Synapse, it's only ever going to happen on your driver. Now, in order to get around that, we have libraries such as SparkML. And SparkML is a distributed machine learning library, and that's where we're going to spend our time today. Super quick on how Spark actually executes. You will submit your query, and your query will go to your driver. Your driver will distribute that query to where your workers are. Those workers will then talk to your data and consume that data in, and they will bring that either onto local disk or into memory. The way that Spark works is it basically doing everything in memory, but you do have options to also store data on disk on those machines. All that data gets read in parallel, and you take advantage of HDFS, or through this example, Azure Data Lake Store, which is a HDFS compliant system. You take advantage of the way that data is natively chunked up into multiple extents so that we can read that data in as quick a way as possible. Now, you do all of your chunking, you do all your querying, and then typically what happens is you may need to shuffle that data around. So your data will get split up into a lot of pieces, shuffled around your cluster so that you can answer your query, and then your query will go back to a single worker and then ultimately back up to your driver to give you the answer, okay? And everything goes through this kind of flow. Right, so let's talk a bit about SparkML. This is probably the easiest machine learning slide you will see in the deck today. But you can think of shallow machine learning in these examples as being typically one of three examples, right? You've got clustering, where we're looking at taking a step back from our data and we're saying, okay, well, what patterns am I seeing in the data? We have regression, which is where we're typically looking to say, okay, well, I'm trying to predict something which is numerical, and I'm going to use all of the other attributes, all of the features, all of the columns in my data to attempt to infer what, what kind of line best fits to that data. And maybe that's a naive example like this one, right, where we've just got a linear correlation there, or maybe it's something a bit more advanced. And then we've got our classification there, which is, looking at a binary classification of fraud and not fraud. Just out of interest, everybody in the comments, just can you just make a note? If you commit fraud, just say, yep, I commit fraud. Just put that one in the comments. That would be great, right? So fraud is something that's quite hard to predict. Fraud is typically something that suffers from a problem which is a class imbalance. And ideally in your data, right, you have a class imbalance. With fraud, and that means that 99% say of your data doesn't contain fraud and only 1% does. And I know as a machine learning developer that I can create you a 99% accurate model, right, for predicting fraud if you have 1% of fraud in your business, by just saying everything's not fraud, right? It's 99% accurate. Ta-da! Okay, so fraud modeling in machine learning is difficult, and there are processes and practices that we can apply. But we just have to be careful of some of that stuff. And we typically break down clustering and then regression and classification as unsupervised and supervised. And that mainly means that in our unsupervised, we're not training towards what's known as a label. I'm not trying to predict anything. I'm just trying to take a step back and infer from what I see. Whereas on our regression, we're trying to predict something numerical, and our classification, we're trying to predict maybe a binary or a multi-class or a multi-label output, okay? All right, let's talk a bit about the machine learning process, right? So I'm going to go away to a number of disparate source systems, and I'm going to get some data. And then I'm potentially going to pre-process that data, clean it up, and then I'm going to spend a huge amount of time potentially doing feature engineering. So really looking at our data and trying to understand what's happening, what can I do to create new features based on other data? How do I address bias? How do I ensure that the data that I have actually fits for the type of model I'm trying to use? And typically this process here, right, is what's known as 80% of machine learning. So 80% of people's time is spent doing this feature engineering, data collection, going back, going forth, in order to build up a data set which is going to generalize to our problem. Now they say that's 80%, and they say the other 20% of machine learning is just complaining about the amount of time, right, that it takes to do that initial 80%. But I always say that 80% is the fun stuff, right? That's where you take your knowledge of machine learning and apply it to a different data set or a different domain. Then we kind of move on to the modeling phase. which is where we might take our data and say, right, I'm doing some kind of binary classification, okay? And I pull in a decision tree and I see how well that works for me. Maybe it doesn't work so well. I pull in a logistic regression model. Maybe it works a bit better. I try a naive Bayes model and it's way worse, and then I have to go back and I just keep iterating until I have something that works. And through that, we go into training and evaluation, where we evaluate each one of those models and see how well they do. Then when they're doing particularly well and we're happy, we might do some hyperparameter tuning, we might do some cross-validation and other techniques, and then we'll put that model into production. So Spark handles that in a slightly different way to lots of other machine learning frameworks. So there are four main concepts. You have transformers, and transformers are something that are looking to take your raw data and transform it into something cleaner or in a different way of working, okay? You have estimators, and now estimators and transformers are very similar, but an estimator needs to be fit on your data. And what I mean by that is an estimator needs to read in all of your data, and it needs to be able to infer a pattern from that data to then be able to apply it back to your data. Now that could be that you've got a column with lots of missing values. And what you want to do is you want to intelligently understand, well, what would be a representative value for that missing piece of data? So in order to do that, we'd have to look at your data and understand it first, and then use that to further populate those missing values. So with an estimator, once an estimator has been fit, it becomes a transformer. That sounds complicated, but just bear with me, okay? Machine learning models are also estimators, okay? We build them, we fit them with your data, and then we transform to get your predictions. And then we have a pipeline, and a pipeline orchestrates this whole process for us. And then we have evaluators to work out if we're doing well or not. Okay, so a couple of examples and a bit more. So a transformer will take in a Spark data frame and it will produce another. Data frames in Spark are immutable. You cannot overwrite them just by interacting with them. You can overwrite them by physically saying, yes, I want to overwrite you. But generally, data frames are immutable, and the ML aspect of Spark keeps that going. So a transformer could convert some data. It could change a categorical value into a numerical value. We'll look at some of that. It could normalize a column. So that is trying to fit your data into a range which is more appropriate for machine learning. And typically we call a transform on a transformer, okay? Sounds fairly simple, right? Here's an example of a regex tokenizer. And a regex tokenizer is a transformer which will take a bulk of words and it will just split them up into individual tokens, so individual words. So here you kind of have, if we have a quick look at what this is doing, right? You've got SparkML, which is the package that we're reading from, and we've got this guy, a regex tokenizer, and that's the function that we're going to use. We instantiate this thing here by saying I want to create this tokenizer, and then we just say, right, I'm going to use that regex tokenizer. Now it accepts an input column and produces an output column. So as the input column it expects from your data frame and the output column it expects to create in your new data frame. And then we just say, well, what's my pattern? You know, how am I actually going to break up those tokens? Then once I have that, I'm going to say, I'm going to call transform on my new tokenizer here that I've created. And I'm going to pass in my original data set here, which is called reviews. And I'm going to create this new data set over here called tokenized data frame. And then if I was just going to display this out, I could just say, right, I want to have a look at that. This will make more sense when we come to have a look at a demo in a couple of moments. Estimators. So an estimator needs to be fit. So we will call fit first before we call transform, and just think it's a two-step process basically with estimators. An estimator may be something like a vector assembler or a vector indexer. Now, SparkML always feels a lot more low level than other kind of machine learning libraries, because you need to, everything you're going to train with basically needs to be encoded as what's known as a dense vector. And a dense vector is a lighter weight way of representing a normal vector, and a vector just being, a series of numbers in an array, okay? And then we may choose our algorithms too. A pipeline just encapsulates all of our processing. And an evaluator is just going to do that, right? How did I get a good prediction? How do we know? If it's regression, we might look at the root mean squared error. We might look at the R squared, the coefficient of determination, to understand if I'm getting a good model. With that RMSE, the lower is better, but it depends on, what your data actually is. Or if it's a classification, we might look at accuracy and try and understand how accurate our model is. There's lots of different kind of competing ideas there for different types of models that you have. Right. Let's have a look at some stuff, right? Okay, so here I am over in lovely Synapse. Let's zoom in a little bit so that you can all see that a bit better. It's a bit zoomed out. That's much better, right? Get rid of these properties. So I have deployed a couple of things. I have already ahead of time deployed a Spark cluster. So I've gone and I've built out a Spark cluster already. I've gone for the cheapest option possible, right? Because you can scale up very high. What scale do you need really depends on the amount of data you have. The thing that you always want to think about as well with Spark is predominantly in memory. It wants to store your data in memory. So when you're looking at machines, by default, Synapse gives you a memory optimized virtual machine. And that's the kind of way that we want to work with. Now, how many of those you need, say, depends on the scale that you want to go to. But typically, unless you're working with huge amounts of data, you can probably keep it fairly lightweight. All right, let's have a little look through some of those transformations and estimators, or transformers, sorry, and estimators. So here I am over in my Synapse Studio, and let's just make sure that Spark is still running and happy. And of course, things start to switch off, right, when you don't run them. So let's just make sure our other one is still running as well. Otherwise, we can just talk through some stuff. So while that spins up, what we're going to do is just quickly talk about how we can work with some of our data. Now, I'm importing pandas here. Now, pandas is a pure Pythonic way of working, but I'm going to need it for a couple of bits and pieces. And that's mainly, in all fairness, to overcome some of the current limitations inside Synapse. So some of what I would expect to see inside Synapse isn't quite available in the format that I would want. So with that, what we need to do is use some other open source aspects to fill in some of the blanks. And we're going to do that with pandas. Okay, that's running now. I've got here my Spark session, so I know that I'm connected to my Spark context, which is basically that driver, right? And I'm going to import a couple of libraries, and then here I'm going to read in some data. Now I'm going to read in some data using this kind of logic here, which says spark.read. So go and read a file for me. It's a CSV. So you're going to find a CSV, and I've got that just deployed into, I've got that deployed, if you zoom in, thank you. I have got that deployed, there we go, into I think that's a data lake, yeah, into a data lake called Synapse ML, which I deployed along with my Synapse session, okay? And I'm saying my file has a header, and I'm inferring schema. And I'm doing this using a keyword argument explosion, okay, which is this kind of thing. So I say here ** keyword args, and it basically will take every item there from my dictionary and then use that further down the line. I could have said option header equals true, option infer schema, option this, option that, but I much prefer keyword arguments, but that's kind of up to you. Here I'm going to call display, and we can have a little look at our data. So we can see here we're working with some house price data, and we've got loads and loads of columns, or in machine learning what we call features or attributes. Then scrolling down, we can see that we've got loads and loads of rows, right? Rows, or what we typically call observations, right? That's the kind of data that we're working with. Now, machine learning models don't like words, okay? Machine learning is basically an awful lot of linear algebra, okay? It's a lot of matrix calculations and deep matrix factorization, which is just basically taking one vector and another vector and multiplying them. So we can't do that with words. So what we do is we do a process called categorical encoding, where we take categorical data, such as days of the week, Monday, Tuesday, Wednesday, Thursday, right? And we encode them as numerical values. And then we keep those encodings so that when we come to reuse our model, we translate everything back into those encodings, and then we use that. So here, let's have a quick look at this particular feature, which is roof style. And so roof style, you know, we've got a kind of like a peaked roof, a gable roof, a hip roof, a flat roof. We've got all these different roof types. Now, when it comes to predicting how valuable a house is, you know, it may be that houses with flat roofs are those kind of trendy square box houses, right? Maybe they're more desirable in particular areas. Or maybe people don't like flat roofs because they're prone to, you know, roofs collapsing and all sorts of fun things. So we want to convert that into a numerical value. And we're going to do that with our first transformer. And you'll see this pattern just repeating, okay? I import my string indexer and I import that from SparkML feature. Then I instantiate my indexer by basically saying, yep, you know, that is equal to this thing. I then pass in an input column. I say how I want my output column to be named. And then here I am going to fit, and then I'm going to transform. Okay, so my string indexer is actually an estimator. I'm going to fit it first, and then I'm going to transform. Okay, so I'm going to run that, and what that's going to do is it's going to take my data frame, this houses df, and then it's going to create this new one here called string indexed df. All right. So we run that. And if you think about what it's doing, it would actually need to be fixed. It needs to go and read the data first. And so what that does is it creates us this nice encoded value here. Oh, lovely, lovely. Maybe we want to go one step further, okay? Maybe we want to do a process called onehot encoding. And onehot encoding gives you the ability to look at categorical values, convert them into numerical values, and then kind of transition them into a format which is far more suitable for machine learning. So as I said, machine learning, lots of matrix computations, right? Lots of linear algebra. So it makes sense to re-encode values actually as matrices. And so what this is going to do, exact same thing. It's going to, you know, take in some input columns, produce some output columns. We're going to fit it, and then we're going to have a look at it. And so here, what this is the style index, which is what we created with our string indexer, and then a onehot encoding of that. And so what this thing is here is this is what's known as a dense vector. And a dense vector is a way of visualizing a normal vector, but with less characters. When we look at 6 things, there's actually more characters. But if you were to explode that out to, you know, several thousand different characters, a dense vector would work very well. So normally, from a onehot encoder, what you would expect to see is an array like this. Okay, so you would expect to see. So for that shed one, it's in the 5th position of 6. Yep, so we'd expect to see 0, 0, 0, 0, 0, 0, 1, right? Because we've got a 0-based array. For that one below, it'd be 0, 0, 1, 0, 0, 0, okay? Many on that. And that gives us the ability to do nice matrix computation because there we've just got a matrix already. Right, so that stuff really helps us with our modeling. It's fairly low level machine learning stuff there, but this is what you do in that 80%, right? Then maybe what we need to do is we need to scale our data. Our data might not be in the right kind of scale for machine learning. So we might want to try and get that into a process which is going to work better for us. And so scaling, right, we've got some fairly large numbers there. And what we typically want to do is we typically want to work in machine learning on a range from kind of 0 to 1. So we want to work on roughly 0 to 1. Oh, that's a 1, but somehow it's got in yellow. All right, okay. So sometimes what we do is we convert that data so it fits on that scale. All right, and we'll come back to having a look at that bit in a moment. In order to scale, I need my data to be in that dense vector. So I'm just going to use a vector assembler, which is another transformer. I'll just show you what that looks like. But basically, it's going to take my data and it's going to put that into vector format. And then it's going to use a standard scaler, which is a way to basically try and take those numbers and take out some of the nuance and some of the depth in them. And we can have a quick look. Standard scaling in Spark is okay, but Minmax scaling works better. Basically, what we have here is you're looking at the you're looking at the original result and then what it's been scaled to, original result and scaled to. And what you can see is we've just reduced it by a factor of, well, we've reduced it. What's that? A couple of decimal places of movement back there. Minmax scaling works a bit better for us. Now, Minmax scaling is that scale on a 0 to 1, or whatever scale you want it to be applied to. And so here what we do is we take that same data in, but I specify my min and my max and the columns that I want, and then that will give you a nice scaled set of data that we can train with. Now, if we run that, so now what we get is all of our values here. So 8450 is now being encoded as a scale on 0 to 1. So everything fits somewhere on that scale. We've got the highest value here and we've got the lowest value there. The lowest value is 0 and the highest value is 1. Now this, you might say, well, why on earth would you do that? And that encodes the exact same knowledge that that has and that has. It's the exact same information, but it's now just shaped in a way that's a lot easier for a machine learning model. So you say, well, it doesn't have the same information as on the same numbers, right? But we're not necessarily interested here maybe in the numbers, but what we're interested in is the difference in the numbers. And the difference between the highest and the lowest and where they fit, that can be more important than the individual numbers themselves. There's a few other bits in here. You can take the log of a house price. Okay, so if we look at house price and we display that, so typically what I would want to do, and this is where some of those limitations are, is I would want to have a look at these house prices and I'd want to come in and make a chart. And you know, I can make a chart and that's kind of good, right? But I need a histogram. I don't need this chart. The closest I kind of have is a bar chart, but I still can't quite get to a histogram, which is what I really need. So I'm going to cheat and I'm going to go and use pandas for that. In order to do that, I need to convert my data from a Spark data frame into a pandas data frame. And I do that by calling this toPandas. And then I just say, hey, pandas, can I have a histogram? And it says, yes, here you go. Now, for house prices, we need our data to be in a normal distribution, okay? And a normal distribution would look something like this, right? Obviously, a paranormal distribution looks something like this. No, just me. What we have now is we have got skew, right? We've got a thing that looks like this that goes on and on, okay? That doesn't work for regression, right? Regression wants a normal distribution. So let's give it a normal distribution by converting these numbers into a logarithmic scale instead of the scale that they were already on. And we can do that by just taking the log 10. And then with that, when we plot that out, we can see that actually what we get is a nice, or at least close to, bell curve. It's a nice Gaussian distribution, right? Right, much better for what we're trying to do. And now when we have that, again, what we've got is the exact same information is here. And we can just go back, right? What we want to do now is we want to try and predict this value, and then we'll convert it back into something which is numerical afterwards. I will skip down a little bit down here just to show you a pipeline, and then we'll look at another machine learning notebook. But what you kind of have here is, so we've gone through a number of transformers, a number of estimators. Now, what I don't want to do is have to worry about each one of these every time being executed in the right order. So what I can do is I could just specify each one of these, specify how I want them to work, my Minmax scaler there, my onehot encoding, and then I can encapsulate them inside a pipeline. And in this pipeline, I set the stages. So the expectation is that I get dirty data coming in and I get nice clean data coming out. And so it's going to do my initial indexing of all of my columns that I need. It's then going to do my vector encoding, my scaling, and my onehot encoding. Okay, so it's going to do each one of those steps that we looked at. If I run that, it's going to encapsulate it all as a pipeline. If I actually run the bit before, and then rather than having to call each one individually, what we just do is we say pipeline fit, so go and read the data, pipeline transform, and it does all of those steps automatically for us. And then we end up with our nice output looking like this. Stop telling me that input df doesn't exist. Which one did I forget to run? You. Thank you. Right. Okay, so we run that, right? And there, now it should actually run our pipeline with our correct data. And then we can produce our output. So this is data that hasn't gone. Let's talk high level through actually kind of what you would do and how you would build out some of these steps into an actual model. So here we're going to do a regression model, and we're going to apply a number of those steps that we've just looked at. So same thing here. I'm going to import some standard libraries. I'm going to read in some data, similar way to before, but now I'm looking at bike rentals. And what I want to do is I want to try to predict how many bike rentals will be needed on any given day in any location. So if we have a look at this data, what you can see is we've got things such as the average temperature, we'll have things like the normal temperature, we'll have the count of bikes that we need, we'll have the year, and our data has all been nicely encoded for us, right? We don't have any categorical values. And this is what we're trying to predict, this count here. I could choose to cache my data and forcibly put it into memory for the entire session that my cluster is up, but I don't actually need to do that. First thing that you want to do, right, when you're working on a machine learning problem is try and get an understanding of what the data is showing you. So we can do that with df.describe, and describe will show us some summary statistics about the data we have. So we can see here, right, that we've got roughly 18,000 observations. And if we have a look at our count, which is the one we're interested in, which is over here, we can see that we've got a mean of 189 and got a standard deviation of 181. We've got a minimum value of 1 and a maximum value of 977. So this immediately screams outlier to me. Because what we're looking at here, if we're plotting a nice kind of bell curve, we've got a line down the middle, right, with 189. If we step out so many standard deviations, we're talking 189 plus 3 times 181, well, whatever that would be. Basically, 977 is a lot higher. So we might want to have a look and see if that's a problematic data point for us, if we want to try and keep that, or if it's just too abnormal for our model, because ultimately, right, we're trying to create something which generalizes. We can have a look at how well correlated each one of our columns is against the count and try to see, you know, well, which columns do we think, which attributes are going to be really useful for us. And so we can see things like here, the average temperature has a 0.4% correlation, which basically, if this is like that straight line is 100%, then 0.4 is something that looks maybe a bit like this. So it's quite well correlated, but on its own, it only gives one aspect of the picture. Whereas if we look at things like this, casual and registered, right, that one is 97% close to that. okay? And now this, if you've done machine learning before, might start ringing some alarm bells, okay? That is too highly correlated to probably be something that is necessarily useful. And what that number actually is, basically, if you add these two numbers up together, you get the count. It's just a different way of working out the count, as whether you're a casual user or a registered user. So those things we would need to get rid of. They are going to add us label leakage. We don't want them. Okay. I'm not going to run a pair plot because it'll take too long to run. Let's skim through some very basic feature engineering. I'm going to create a new column where I work out the time of the day. So I'm just going to add that one on to the end. Further down, time of the day, so that I can see if it was rented in the AM or the PM, and maybe, you know, that is important for us. So if we have a look at, let's try and make a chart. Let's make a chart where we look at the hour. Right, there we go, hour, not the year, thank you. Our values will be our count, and we'll look at the sum, right? So generally what we can see here is that time appears to be really important, right? There are lots of rental in the early hours of the day, there's a bit of a lull at lunch, and then there's lots of rentals that kind of then start to peter away, you know, further throughout the day. Lots of people cycling home maybe from work. That's really useful to see. Got our time on there, our AM, PM. And now we'll get into our machine learning. So we have got a label that we're optimizing towards, which is count. And so here we're going to be doing supervised learning. And with supervised learning, I do testing and training. I do a test split so that I've got some data that my model has never seen, and I'll use that for evaluating. Here I'm going to start doing some of those steps that you saw before, which is where I'm importing some transformers and I'm trying to scale my data so that it's appropriate for what I'm looking at, for what I'm trying to train with. Now, lots of this data is already scaled, so we kind of don't need to worry about it. I'm going to import a decision tree regressor. So decision tree regressor is you kind of start off with one bit here, and what you're doing is you're making multiple different decision points until you ultimately come out with some kind of prediction, 16 bike rentals. So with a decision tree, it's not something that kind of fits on a line like this, where this value is, where one value is that and the other value is that. It's a decision tree, so you get lots of repeating values, which can be problematic. So we'll run that. We will set the label that we're trying to predict towards. Going to create a pipeline here, right? Same as before, this time ending up with my decision tree. And then I'm going to fit the pipeline to my data. And when I do that, I'm going to create a machine learning model. So that's going to run. This is going through the process now of training that model. It's a fairly naive model, so it doesn't take too long. We can export that model should we want to. And then what I can do is I can take a new data set, so my test data set that it has never seen before, and I can get some predictions. So I'm creating a new data frame by transforming my test data. And what we can do is we can start evaluating that to see how well we're doing. So we're going to look at the root mean squared error and the R squared, the coefficient of determination. And what we're looking at there basically is, again, if you imagine a thing like this with a line, and I make a prediction here and a prediction here, we look at the distance between these lines of our prediction and our actual, and then we take the square of each of them, and then we take the root of all of those, and that gives us an approximation of how bad our model is. So this model here is 108, which is pretty bad, okay? At this point, without doing any more work, it's on average wrong by 108 bike rentals. Given that the mean is 189, that's quite significant. Now, if I can share this one with you, you can have a play around with it and get it down really low by changing a couple of things and doing a little bit of feature engineering. This is an example that we run when we run training. We then give it to you to actually go ahead and try out some different things and see where you get to. So with that, there you go, we can see that our mean is 189. And then we can just have a look at some of our predictions and see how well we did. So we know that it's slightly off.
We need to wrap up very soon.
I know, I'm almost done.
All right, okay.
So we have got an actual of 22 and a prediction of 62, right? And you can see these repeating values because that is where we've got our decision tree kicking in. Now we could switch that out for a different model and get something a lot more aligned with different values closer to what we're working with. So that was a rattle through how you can do machine learning in Synapse. But once you have that model, you can save that model back down to your lake. And then each time you want to rework it, you can just import that model with your data, hit transform, and it will take your raw data all the way through to give you nice, clean predictions, which you can then push off to your decision support system, such as a warehouse, or give to an end user to interact with. So I'd say that Spark is great for many data analytics tasks. And where you want to do machine learning in the cloud is definitely my go-to for batch machine learning. However, today, maybe Synapse isn't the best place to run it. There are alternatives, right? Such as one also on our screen there. So just think about what you're trying to achieve. Other alternatives, right, are Azure ML, trying to build something in Azure ML and factor that back in. But Spark is very good for that stuff. My details there's my email. You can get me at SQL Shark on Twitter as well. If you have any questions, then let me know. Ta-da!